Hello, everyone. Today I'm going to introduce my Python code for the undergrad course, Compressible Flow. This can be used to replace the tables. And comparing to the tables, the code is going to be much faster and more accurate because you won't need to do the interpolation or finding which line is which Mach number anymore. In addition, the code is really easy to build and will be in minimalist style. Okay, let's first see a couple examples of solving problems with the code. The first question is about normal shock. Given the pressure 1, T1, and Mach number 1, and find pressure 2, temperature 2, and PO2, TO2, and delta entropy. So what is pressure 2? It's going to be the ratio across the normal shock times P1. This one is determined by M1, so M1 equals 2.7. It gives us this number times 1 ATM. So this is simply just that. Temperature 2 equals to the temperature ratio across the shock wave times T1 equals to this number, this ratio, times 288K. And this will give us this number. Okay. Next, total pressure, PO2, equals to PO2 over PO1 times PO1 over P1 times P1. And PO2 over PO1, this ratio, PO1 over P1 is the isentropic relation with Mach number equals to 2.7. So this. Let's get the result. This is just like that. Next, it's temperature, total temperature. So total temperature 2 equals to total temperature 1. And that is simply the isentropic relation between TO1 and T1 times T1 equals to that times 288K. All right, the last one is delta entropy. This is equals to negative R times log PO2 over PO1. And this is simply 287 times log this number here. And this will give us import math negative 287 times math dot log that. So 246.53. The unit will be consistent with R. So this is joule per kilogram per K. Okay, let's move to the second question. It's about oblique shock. So we know the theta, we know M1, we know the pressure, static pressure before the shock, we know the temperature. Let's find wave angle beta, P2, T2, and Mach number 2. So beta is coming from the function or the relation between Mach number theta and beta. And in my code, it's oblique shock. Yeah, just give it theta. And our theta is 22.5 degree. Mach number 1 is 2.5. And we are only looking for the weak solution. And here we find it that beta equals to this number. Next is pressure 2 equals to P2 over P1 crossing the oblique shock times P1. And this ratio is here. Times P1 is 4 atm. And this gives us 14.58, 59 atm. Next, temperature 2 equals to T2 over T1 across the shock wave times T1. And this temperature ratio can be found here times 210K. Next, find the Mach number 2. Mach number 2, in my code, I just give the Mach number 2 directly. But if you are using the table or if you are doing your homework, your lecturer probably expect you to calculate by hand. We get the Mach number 2 in normal direction from the normal shock relation. So you can either use that to derive it or just use this number from the code. But if you want to derive it, it's going to be m2 equals to mn2 divided by sine beta minus theta. Mn2 is this number from normal shock relation divided by sine beta is this minus 20.5 degree. And because this is in degree, so we want to divide it by 180 times pi. However, in Python, I think if we want to use sine, we need to use that. It's in this package. Oops. Yeah, it gives us Mach number 2 equals to 1.522. Let me check. Okay, they are the same, so that means it should be correct. Let's move on to the third question. There's an expansion waves and then followed by compression. For expansion waves, we want theta 2. And for this one, theta 2 is 20 degree. And the question is asking for P3. So let's first see what is P3. So P3 equals to P3 over P2. So this is the oblique shock times P2 over P1 times P1, and P1 is given. So P3 over P2, this can be found from Oblique Shock. And P2 over P1 is the shock wave expansion waves. So crossing all of the expansion waves, this process will be isentropic, which means PO2 equals to PO1. So they are related based on the total pressure. So P2 over P1 equals to P2 over PO2 times PO2 over PO1 times PO1 times P1. The first one is basically a function of Mach number 2. This one is a function of Mach number 1. Here we first find Mach number 2 because Mach number 2 would give us this number and also this number. And to find Mach number 2, we need this theta 2, which is 20 degrees, and Mach number 1, which is 3. So theta 2 is 20 degrees. Mach number 1 is 3. From that, we get Mach number 2. So M2 equals that. And this gives us Isentropic relation. M equals to that. This gives us this number. However, it's 1 over that because it's P2 over PO2 times, this is 1 because they are the same. PO1 over P1 is Mach number 3. So what is this number? Now we have an oblique shock, and the first Mach number is this one, and theta is also 20 degrees. Theta is 20 degrees. Mach number, this one, is that. And the pressure ratio is the only thing we need. So finally, P3 is that, this number, times this number, times 3 ATM. Okay, I hope you like this code, and if you do, you may continue this video to see how I built it. So first, let's start a new project on PyCharm. I have already deleted all of the unwanted lines, and only this line would remain. The first thing I would like to do is print a welcome message. Simply just compressible flow and by my name. And then the first step is to build the isentropic relations. Before that, I would like to import the package math because we are going to use sine, cosine, and log. And we can define the error constant here. They are going to be global variables. So R is 287, gamma is 1.4. And for convenience, I will just have pi equals to math.pi. So for isentropic relation, and we will define Mach number to POP, ROR, and TOT. We take the argument to be the Mach number. And we write down the formula for these three ratios. So this one is gamma minus 1. So this function will return a tuple that has three elements. The first one is the total and static property ratio of the pressure. The second one is total density over static density. The third one is temperature. Let's give them a test to see if these return values are correct. Define testing. Let's test three different cases. One is subsonic, so giving it Mach number to be 0.5. And a sonic case, and a supersonic case. And let's run it. So the printed out three different tuples. The first one is always pressure ratio. This one is density. And the last one is temperature. Here, we can compare the results here with the numbers on the table to see if the values are correct. I'm going to compare them here right now. All right, they are indeed correct. So let's move on. And that means my function for this one is correct. However, I would like to print out in a better way other than this tuple. So define, I'll call my function define and print isentropic. First, I will print this is an isentropic relations. And then I print out the variable names, including Mach number, pressure, density ratio, and temperature. Next, I print the variables. And I think 7 digits would be enough. I have 4 of them, so I just give it 4. And dot format. I pass the variables here. So the first one is Mach number. The second one is this value, this tuple, but I only take the first value. Similarly, this one is the second, and this one the third. So instead of printing the the tuple, we will just use and print that for the 3 cases. And I can remove these 3 lines. Call it. Okay, I would like to print another blank line. Yeah, they look pretty good. So this is our isentropic relation given by the Mach number, and the program will give us the ratios. However, what if we have the ratios and we want to have the other 2 ratios or the Mach number? So we will define other functions like that. This one can be explicitly written down. So I'll just define here tot to m, passing by a tot. All right, let's test them. So for the case with Mach number equals to 1.5, we have pressure ratio to be that. And that means we expect this to give back our Mach number to be the same, which is 1.5. Similarly, this one can be that. $1.45. See, all of them give back the Mach number that is close to 1.5 with some error. That's because our digits here are not enough to give back the same exact values. However, they are very, very close to the 1.5. I think they are accurate enough. So that means our isentropic relation, finding the ratio from m or finding n from other ratios, are correct. Next, let's move on to normal shock relations. First, define m1 to the variables you can find on the table. So these are P2, P1, row 2, row 1, T2, T1, PO2, PO1, and Mach number 2. And we give the function the Mach number 1. So the last one, PO2, PO1, is kind of tricky because we will need some isentropic relations alongside with the normal shock relation. So P2 or PO2, PO1 would equals to PO2, P2 times P2, P1 times P1, PO1. But what is PO2, P1, P2? It's the isentropic relation with the Mach number equals to M2. And we only take the first value, which is the pressure. And what is P1, PO1? It's 1 over the isentropic relation with Mach number equals to M1. And again, we only have the first value. Oh, this should be that. Okay, now we return all of these values. And we test them. Here we can only test them on supersonic cases because M1 has to be supersonic, or it can be sonic. So let's test these two different cases. Run it. Oops, I forgot to print. Yeah, for the Mach wave, everything is just 1.0. And for this one, let's Mach number is 2.0. Okay, they are consistent with the table on the textbook. So that means our function for this one is correct. These values are correct. Next, I would like to print the result like before. So define M1 print normal. We give it M1. Just copy this to here. And here we have other values like P2, P1, row 2, row 1, T2, T1, PO2, P1, and Mach number 2. We have two additional variables. And here, I would rather let the function run for once. So I will just call it return equals to M1 to that and passing it M1. So this value would be a tuple of all the variables. So this one is Mach number 1, and this one is return, but I only have the first value. Okay, let's test it. Something is wrong. Tuple index out of range. 0, 1, 2, 3, 4. There should only be 4. Oh yes, that is the case. Okay, the printout version seems to be all right. So let's deal with the inverse function. So what if we know one of the ratios and we are trying to get the other ratios and then Mach number 1? So this is slightly more trickier than before because we do not have an explicit function for M1 given by the other ratios. Instead, we are going to solve it by an iterative method. For this one, I'm going to use bisection. I'll call my function just inverse, because it's basically in an inverse function. There are 4 arguments. The first one is function, the second one is a target, and the lower and the higher limit, upper limits. For bisection method, we have to make sure that first is continuous. Then the function is monotonic in A and B. Third, FA and FB are on the same on the different side of the target. That means one is larger, the other is smaller. All right. So if we are sure of these 3 conditions, we can move on. We can use this inverse function. To define the bisection method, we would need a maximum iteration. Give it a larger value to be 80. We need tolerance. We need the error, current error. Initially, I just give it 1.0. And we need a current iteration number to be, it can start from 0 or 1. That depends on your code. And C is going to be our return value. And at this moment, it's just none. Before we start the algorithm, we have to make sure that FA and FB are on the different sides of the target. So FA is function passing by A, and FB is function B. We have to make sure that FA and FB have some values instead of just like none or something. So if either of them is none, we have to stop the function. We will print out cannot find solution, and then return none. If A is already really close to our target, we simply return A. Or if B is already really close to the function, our target, we return B. Of course, if A and B are on the same side of the target, we won't be able to find any solution. So print cannot find solution. Return none. So now we can begin our algorithm. So while the absolute value of the error is larger than tolerance, that means our value C is not close enough. So we update the C value to be in the middle of A and B. And we update FA to be that, FC to be that. We update the error to be the absolute value of FC and target. Okay, if FA and FC are on the same side of the function, on the same side of target. That means FC and FB are on the different sides. So the solution would be between B and C. So let's replace A with C. Otherwise, replace B with C. So during each iteration, the range between A and B will be reduced by half. And eventually, we should find a solution. However, sometimes we just cannot find the solution, and we have to make sure that there's a way for the code, for the program, to jump out from the while loop. So we update the iteration number, and we increase it. And if that number is larger than the maximum allowed number, we are going to print out, okay, we cannot find solution, and just return a null value. Other than that, if we jump out here to here, that means our error is smaller or equal to tolerance. That means we find a satisfactory value of C, right? So FC is close to the target. This value is smaller than tolerance. That means C is what we are looking for. Therefore, return C. Okay, let's see how we can implement this this function. Oops. So let's test with Mach number 1 equals to 2.0. For now, it will give us these values. If we know PO2 over PO1 to be this value, it should give back Mach number equals to 2, right? So M1 equals to, we are using inverse. And the function we are here, I'm going to use Lambda function. And we only want this is 0, 1, 2, 3, this element. The target is going to be this value. And the lower limit, it can be start from 1, because for normal shock, M1 has to be supersonic or sonic. So starting from 1.0 to, I give it maybe 99 is large enough. And let's see if M1 is indeed 2.0. All right, you see that the result is close enough to 2.0. By testing that, we are sure our inverse function works pretty well. And I'm going to explain briefly what this lambda function is. So this function just simply an inline function in Python. The other way to do that without lambda function is I will have to define a function. So this function, I will call it M1 to PO2 PO1, right? I pass by the argument to be M1. And this will return PO2. So what is PO2? PO2 is just this function. But we only want this element. So I call it M1 prime. And here we have that. This should give us the same value, right? They are exactly the same, which means writing down lambda x and this whole thing like that is equivalent to define another function and use that function here. I would prefer to use lambda function because if we are going to do this for PO1 and PO2, That means we have to do 4 other things, and we have to define 5 more functions for that. And I just think lambda function is much more convenient here, so we don't have to define any more function for the inverse one. So let's just remove it here. What have we done till now? So if you give me P2, P1, I should give you back M1 function. And then I can print out this value. So for example, if your question give you M2 to be, it has to be subsonic. So let's say 0.2. No, it cannot be that low. So 0.8. Okay. And what is M1? M1 is this function only return the last value. So -1. And our target would be M2. And our lower limit and higher limit, upper limit, I'll just keep it 1 and 99. And then we can print out the flow by that given M1. Let's see our result. Sorry, I forgot to print. Oh, yeah, my bad. Print normal. Let's see our result. See, now given by the Mach number 2 is 0.8, we should be able to find M1, and then we can find all of the other variables from this function, right? So if you give me the temperature ratio, so T2, T1 is that, and we change the target to T2, T1, and we change this function to be 0, 1, 2, to be 2, and we should expect the same value, right? So yeah, Mach number 2 is 0.8. This is how we implement the inverse function. And now we are able to find M1 with any of these values and print it out like that. So we are done with normal shock. Normal shock relations are done. Let's move on to oblique shock relations. There's only one equation that is the core of everything about oblique shock, that is Mach number, theta, and beta relation. So here we have defined, given M1 and beta, we can have what is theta. According to the equation on the textbook, it's going to be tangent theta because this value is tangent theta, so we have to use a tangent to get what the true value of theta. Therefore, return mass.a tangent theta. Okay, let's give this value a try. Give it a Mach number 1 to be maybe 2, and beta to be maybe 75 degree. However, this equation, everything here, both beta and theta are in radian. So we have to find a way to convert between radians to degree or degree to radian. So for convenience, I have radian to degree. Just like that. So everything here is simply beta times degree to radian. All right, run it. Print this out. And yeah, we have to convert it back to degree. So this is about 20 degree. Let's compare with the diagram on the textbook. Yeah, it's slightly smaller than 20 degree. Maybe try another one. So beta is 5 degree, and the Mach number is 1.7. This should give a result that is similar, that is close to 12 degree. Yeah. All right. I think this function is correct. Next, we are trying to find, given Mach number, theta value, we will try to find beta value. First, let's observe this function. Beta is not an explicit function of m1 and theta. Also, beta is not an monotonic function of them. So if we observe the function or the diagram on the textbook, we find that for a given Mach number, the valid beta value is between mu, which is Mach angle, to 90 degree. Theta is increasing from 0 to theta max, and then decrease to 0 again. So theta is no longer a monotonic function of beta for a given Mach number. That means we cannot just simply implement the bisection method here. However, if we divide the region into two, and one is from 0 to theta max, the other is from theta max to 0, and we find the corresponding beta value to be, beta is from mu to the beta value that is corresponding to theta max. Then, in this region, theta is a monotonic function of beta. And in this region, theta is also a monotonic function in this region, right? So then we can implement the inverse function here. So our first task is to find theta max, as well as the corresponding beta value. So let's first make this a comment and find m1 to theta max, as well as the corresponding beta value. And this one, we only have one argument, that is m1. So we know that theta is only increasing and decreasing once. It's not like it's increasing, decreasing, and then increase again. So say if we have 4 values, A, B, C, D, for beta. And for theta, is going to be like FA, FB, FC, FD, right? If we know that FC is the maximum value, then we are sure that FC is the largest value between in all of these four values. We are sure that theta max is between B and D. Why? Because it's before B, then it's first decrease, and then from FB to FC it's increased, and then from FC to FD it's decreased. And that's not happening in our case. It's only like increase and then decrease. It will never increase again. So similarly, if we are sure that FB is the largest value between in all of these four, that means the theta max is between FA and FC. So now we can just replace FD to FC, and the region between FA and FD is going to be smaller. It's going to be like smaller, yeah. And then we can do it iteratively. And finally, FA and FD would be so small that it doesn't make any difference. So this idea is very similar to bisection. We are going to have the similar variables, so I give it a maximum iteration to be 80. Tolerance can be smaller, like 1e minus 9. A current error to be 1.0. Current iteration number is 0. And let's give it the initial value for A and D. So the A is simply mu, which is A sine 1 over Mach number. D is pi over 2. And B and C are just none. We first update B and C values. B is equal to the range between A and D divided by 3 plus A. And C is going to be D minus this. And we update function, we update FB and FC. So like that. As I just explained, if FC is larger than FB, if FC is larger than FB, that means theta max is between B and D. So replace A by B. Else, replace D by C. And again, we have to make sure that the program will not just stuck here. We have to make sure there's a way for the program to jump out of the loop. So iteration, we increase that by 1 and check if that number is larger than the maximum value allowed. Print cannot find solution, or you cannot find maximum theta max. Return none. Otherwise, okay, I have to update error. Error is the difference between C and B. So what does it mean if the program reaches here? That means C and B is so small that it is smaller than the tolerance. It's already accurate enough. So return. Like our function name is theta max and then beta. So we return theta max. Theta max is going to be so B and C are beta value, and theta max is going to be, we have to use that function to find it. We can use either C or B because, as I mentioned, they are really close. They are smaller than this value, the difference between them. So yeah, use that and B. And let's test it before we move on. So for Mach number 1 is 1.7. Theta max is about, oh, there's one thing. Both of these are in degree. So theta max and theta max are this value. But we would like to see them in degree. So the theta max is going to be 17 degree. For Mach number 1 is 1.7. That is correct. And the corresponding beta value is going to be 65. Yeah, that is correct. So once we find the theta and theta max and the corresponding beta value, we can then use the inverse function or bisection method to find beta from Mach number and theta. So first thing is find these two values. And now we can use inverse function. But I would like to give it a tolerance. And first I will just print out, okay, this is a oblique shock relation, right? And if 0 is between theta and theta max, then we can continue find the two solutions. However, else if theta max is smaller than theta, but theta is smaller than this, which means theta is really close to theta max, we will only have one solution. For this one, we will find strong solution. And we will find weak solution. And for this one, there's only one solution because theta is really close to theta max. This is why I put a tolerance here, because our theta max is not going to be exact. There's a tolerance that is similar to that, right? Close to that. So maybe the question just give us the exact theta max value, and our method, our algorithm fails to give an exact function, exact value for theta max. And it will tell you that, okay, theta is larger than theta max. That means there's no solution, but there is actually one solution. It's just the theta max solution. So that's why I put a theta max plus tolerance here. Max solution. Okay, this case is really rare that I have never actually used this one. But just put it here and in case else. So if either this or this is the case, that means theta is smaller than 0, which is not making any sense. Or theta is actually larger than theta max and the difference is beyond tolerance. That means we cannot find a solution, right? Cannot find solution. Oops. Okay, let's first find this. We will just print M1, beta, and theta solutions. Because now we have beta, theta, and M1. They are just here, here, and that. So I would like to find a way to print all of them. So M1, theta, beta, print. And I'm going to use all of them. So M1, theta, max, beta, theta max. And I will write another function. Define this. Because this function is going to be used here and here twice, that's why I write down another function for that. So we will print out just like that. And the variables are going to be Mach number 1, theta, and Mach number 2, and then beta, and Mach number 2. But we do not know Mach number 2 yet, so we have to find it. To find it, Mn1 is going to be M1 times math sine beta. And Mn2 is find by the normal shock relation. And we only take the last element, which is M2. And M2 is just Mn2 divided by math sine beta minus theta. All right, we find M2. Let's try it here. Okay, so this is a theta max value, and for here, we are going to find M1 strong first, right? Oh, not M1 strong, beta strong. It's going to be the inverse function of this formula. with target to be theta. The range, so for strong solution, the range is between beta-theta-max to pi/2. And then print all of them. We know Mach number, we know theta, we know beta, theta, we know beta strong. Similarly, the weak solution for beta is okay, these are the same except the range. The range is going to be from mu to that, and mu is simply one over Mach number. Yep, and let's print it. And let's try it. The function is called m1 theta to beta. So theta, we give it a small, oh, okay, Mach number 1 should be probably larger than that, maybe 2.5. We are making sure that there is a solution. So theta can be smaller than that, a smaller value can be 12 degree times degree to rad. Let's test it. Okay, there are two solutions, but you see that I forgot to convert these two values into degree. So they can be changed here, rad to degree. Rad to degree. And let's find the values on the diagram to see if these values are correct. Mach number is 2.5. Okay, there isn't 2.5 on the diagram. So let's try 1.7. And theta is just 12. Okay, beta is 50 degree. This is value we have seen before. So this is correct. For a strong one, it's 78 degree. Yes, that is correct. Let's see what if there's no solution. So if we give it really weak supersonic flow. Yeah, cannot find solution. Okay, so for the three value, Mach number, theta, and beta, if we know Mach number theta, we can find beta. If we know Mach number beta, we can find theta. So what if we know theta and beta? So this is a really, I would say it's really rare situation that we know the two angles but not Mach number. But I'm still going to solve it. So theta, beta to Mach number. So the minimum Mach number can be found if beta is just the mu, which is Mach angle. So like that. And using this function, we can find it. So for given beta, we are trying to find the Mach number, and the target is going to be theta. It starts from M1 minimum to a really large value. It can be 99. Return M1. Again, let's test it. So for our previous test, Mach number is 1.7, theta and beta are these values. So now we are going to use this value and convert it into radian, and to see if the function will give us back to Mach number equals to 1.7. So theta, beta to Mach number 1, and we have theta, we have beta, and we print it. All right, it's really close, which means our function for this one is also correct, or they are consistent to each other. Okay, let's go back and do a little more than just printing this. So for all of the three cases, which one is the most frequent? It's this one is more natural. Sorry, I mean this one is more natural. So we know the incoming Mach number, we know the deflection angle, and we don't know the beta value, the wave angle, the shock wave angle. And at this moment, we print something like that. I think it's good enough, but maybe we can do a little bit more. First, let's adjust this value's position. So beta can be moved by 3. And Mach number. All right. What else can we print out? We can print out the normal shock relation across the oblique shock, right? So we can also print out the isentropic relation before the shock wave and after the shock wave. So this is M1 and this is M2. Yeah, we have all of these 4 relations. But I think I would like to improve it a little bit. First, this is not normal shock relations. This is oblique shock relations, right? And second, this one should be M1, or this one should be fixed. I'll change that first. This one is M1. So for oblique shock, I would like this to be MN1 and this one to be MN2. And here, it's not called just isentropic relations. I wanted to call just this is M1. This is upstream, right? M1, PO1 over P1, rho O1 rho over rho 1, and this one the same. And this one I'll say it's downstream, so M2, PO2 over P2. So first, let's change this. I will tell this function that okay, this is actually oblique shock. So I'll pass another variable, another argument, and by default, this value would be false. So this won't mess around with our normal shock relations. And if this one is oblique shock, then I'm not going to print that. We are simply going to print this and make it mn1 and make the last one mn2. Else, we print this and that, and then followed by the variables. Let's see if this is correct. So now it looks better. It's mn1 and p2, p1 something, and at the end it's mn2. And let's change this one, the isentropic printing function. I'm going to remove this one here. Isentropic. So I'll tell the function that this is an upstream equals true. Similarly, I'll tell it this one, this is downstream equals true. And we will add these two arguments, is upstream. And by default, this one is false. Downstream, this is also false. So if this one is upstream, what is it going to print? It's going to print this is upstream. And this one is M1, PO1 over P1, rho O1, rho over rho 1, PO1 over T1. Else, if, it's L if, is downstream. And everything is changed to 2. Else, it will print out the original one. Okay, let's see. So this is a strong solution. Upstream Mach number relations, isentropic relations. Downstream, and this is weak solution. I think it looks all right. So we are done with the oblique shock relations. Next, we are going to build the expansion wave. This one is easier. There's only one function, that is mu. So define m to nu, given the Mach number. And this one, 0.5. This one, square root. And the nu is just a times math a tangent b over a minus math a tangent b. Return the new value. Again, let's test it. It has to be larger than 1. So can be able to find in table 5, A5. So Mach number is 1.7. U is okay. In this equation is in radians, but on the book it's everything is in degree. So convert it into degree, and 17.8 degree. This is consistent with the book. All right. Now we have new. We should be able to find Mach number 2 with that. So the case is that we have theta 2, the expansion angle, and we usually know the Mach number 1, and let's find Mach number 2, right? So theta 2 is given. Mach number 1 is given. Nu 1, that is simply this value, and nu 2 is theta 2 plus nu 1. And m2 is going to be inverse of this function, m2 that nu 2 1. Starting from, we search from 1 to a really large number. Remember that Mach number has to be larger or equals to 1 to have it here. Otherwise, this number would be negative, and B would be complex number, and that's not what we want. So we can find M2 here. Let's just print everything here. So print, this is an expansion waves. And let's print out our variables. M1, nu 1, theta 2, nu 2, and Mach number 2. So we will have 5 values. They are going to be M1, nu 1, theta 2, and nu 2. Finally, M2. All right, let's test it. So M1 equals to 1.7, and theta 2 can be, say it's 13 degree. And theta 2, M1 to M2, and we have theta 2, we have M1. Let's test it. Theta 2 is 13 degree, nu 2 is this number plus this number. And we find M2, and that is larger than M1. It looks all right. Maybe I can move this one a little bit. So this one is moving back 1 space, this one is another 1 space, this one is another 1 space. All right. So define Mach number to AA star. AA star squared is going to be All right, let's test it. Okay, this should be able to find in table 1, table 8.1. It's 1.338. Yes, this is all right. And we would like to print this also in isentropic relations because it's also on the table. So with that, we find our mprint here and put it here, isentropic relations. So A over A star is just like that. So let's print it out. And this should be consistent with the table. Like maybe we can change it to 2.5. Oh. .637. Okay, that is correct. Everything is consistent with the book. Yes. Okay. Let's find the inverse function for that, right? Because sometimes we know AA star, but we don't know a Mach number. Define AA star to M. Okay, there are going to be two solutions. One is M supersonic solution. The other one is subsonic. So I'll just call this super sub. The subsonic solution is going to be that. It's going to be, we are searching from a small number to sonic solution, to 1.0. For supersonic, these are the same, except we are searching for the solution from 1 to a really large number. And I'll just print everything here. So this is a quasi 1D flow. And we will print out AA star, M super, and M sub. Print. This is going to be columns.c7f, 3 spaces, dot format. It's A star, M super, and M sub. So let's try it. Remember this value, AA star, has to be larger than 1. Let's say it's 2.3. Actually, let's try this value for AA star. This should give us back to the Mach number to be 2.5. So, yep, 2.5, which is the supersonic solution. The other one is subsonic solution. All right. Now we can replace the table 8.1, 8.2 for normal shock, 8.5 for expansion waves, and the diagram for Mach number, theta, and beta. We can just use our code for all of these three tables and the diagram. However, every time we are trying to find something, we are going to use change the code and then edit the part of the function that is running. It can be testing, or we can just run it here to find maybe the A star value or the normal shock relation. I would like to make it such that we do not have to change the code ever. Every time when we are running the code, it will give us a prompt to saying that, okay, what value you know and the name of the variable. For this one, if we are trying to find the normal shock relation, and if we know the pressure ratio across the normal shock, we can just say P2, P1 equals to, it has to be larger than 1, so maybe 3, and it will give us back our normal shock relation, and P2, P1 is indeed 3. So if we want oblique shock relation and we know theta, the deflection angle is maybe 17 degrees. And we also need to know the Mach number 1, and let's it to be 3.2. It will give us the strong solution and weak solution. So if we have this prompt and in an interactive way, we do not have to run the program once and once again, and we do not have to change the code ever, right? So I'm going to write this interactive part for the code, and we are going to delete that. Interaction. All right, define a function called getInput. This is just prompt. And first, I would like to print a lot of equal signs that can be seen to separate different inputs. And first, we will get input. This is simply by this input function, and call it, give me a variable name, and give me the value of that variable, right? And the result, or the input that is given back from the user, is going to be split by equal sign. And what's next? If the length of input, remember it's already been split by the equal sign. If the length is 1, that means there's no equal sign, or there's nothing before or after the equal sign. That means there's only one word, right? So if the length of that is 1, then first let's make sure that this the string, we use stripped to remove the white spaces before or after it, and make it lowercase. So let's check if s is quit or exit. This is simply we just quit the whole program. Else, if s is help, if this string is help, or for convenience, we just type a question mark, then we will print a help message. We will define it later, but we will just write it here. I need help. All right. And if this is something else, at this moment, I will just say, okay, it's wrong input format and return. So nothing is done. Let's give it a test. So here, I'm not going to use that. We will call it while true. Get input. Yeah, like that. So if I have something here, it's going to be wrong input format. If I have help or a question mark, it will say, okay, I need help, or whatever the help message is. It can be there can be some spaces between them, right? It's the same. Or it can be just exit. The letters can be either lowercase or uppercase. It can be even a mix between them, like that. And there can be spaces. Okay, it just exit. So this is correct. We have done the part that the length of the input is just 1, so there's no equal sign or nothing between, nothing before or after the equal sign. But normally, the length of that should be 2. We expect it to be 2. Let's call the name of that is this, right? The variable name is that. And the value is going to be, we convert the string into float. So it's imp. Second one, right? However, here I would like to write another function, another helper function for that. This is because sometimes when we have a wrong input for that, like a number float equals to float, and the string is 1.2. This is correct because 1.2, this string can be converted into a float number. Yeah, so this is correct. So what if we have something like 1.2.3? Then the program will crash. So we would like to put like a guardian for that. In case that the program just crash, we will print out, okay, your format is wrong. Then try again. For that, we define another function for string to float, and we take a string for that. Try float equals to convert it into the string into a float. Sorry, we used strip. Yep. Return the float number. Or if we encounter an exception, which of the type value arrow, we return none. Now, for the same case, if we tried it here, if the string is 1.3.2, the program will not crash. It simply returns a non-value, right? So the program will continue, even though we know that 1.2.3 cannot be converted into a float number. All right, let's implement that. Value is going to be string to float that. So what if the value is none? That means our format for the string, our string for that cannot be converted into a float number. That means our format is wrong. So wrong input format. Try again. And return. If that is indeed not none, that means value now is a true value. It's just a float number. So we can see what the name of the variable is. So if the name is, let's start from isentropic relation. If the name is Mach number, we are going to print out the isentropic relation, and Mach number is its value. Easy, huh? Else if the name is, what else we have for isentropic relation? It's a pressure relation. We will first solve the Mach number to be POP to M with value, and then we print out that and solve. Similarly, we have name is row O row, and this is going to be the same. Yep, let's give it a try. So we have maybe Mach number is 2. Yeah, it will print out the isentropic relations for M, the Mach number equals to 2. So what if it's the temperature ratio equals to 1.8? Yeah, it gives back the same thing because that is the same case. What if we have a wrong input? For example, we have POP1 or something equals to whatever. We're just not printing anything because it doesn't recognize POP1. All right, this is isentropic relation, and the next is normal shock relation. For normal shock, the core is Mach number 1, right? So Mach number 1, print normal and value. Let's see. M1 is 2.7. Yeah, correct. And if the name is these things, for example, P2, P1, we are going to first solve M1. And this is going to be using inverse function, the lambda function, x, M1 to that, with x at the input, and we only take the first value, so 0. The target is going to be value, and the range is from 1 to a really large number. Then we print the solved M1 value. This is for P2, P1, and it is the same for all of the other things. Row 2, row 1, this one is going to be 1. For T2, T1, this is going to be 2. For PO2, PO1, this is going to be 3. And at last, if that is Mach number 2, this is going to be the last one. This can be 0, 1, 2, 3, 4, or you can use -1. They are the same. All right, let's test. So if M1 is 2.3, it will give us this number. And if M2 is this, Yeah, it gives us back the same thing because they are the same case. So what if M2 is 0.7? Yeah, everything seems to correct. So maybe PO2, PO1 equals to, it has to be smaller than 1, right? So 0.8. All right, seems to be correct. This is for normal shock relation. And what next? Next is oblique shock. So if name is beta, and we convert it into degree, into radian. So, however, if we know beta value, we still need Mach number or theta value. So we will ask the user to give us what is the Mach number? And if the user indeed give us back a correct Mach number, that is here, theta can be found from this equation, right? So we now know Mach number 1, we now know beta. Beta is given by here. We will find theta here. But what if the user does not know Mach number 1? Then he or she has to know theta value. So input theta equals to what? Again, if theta is not known, then, well, we cannot move forward. So print wrong input format. Try again. Otherwise, we would know theta, but we don't know Mach number. So we derive Mach number from this equation, theta beta. Oh, there is one thing. Theta here has to be converted into radians times degree to radians. So no matter if M1 is known or theta is known, we should be able to know everything now, right? If M1 and both M1 and theta are not given, it will just return. So we don't have to care about that case anymore. Now we know all of the three values. We will print. This is an oblique shock relation. And we are going to print everything from this. M1, theta, beta. Okay, let's try. So if we know beta is 75 degree, and Mach number 1 is, let's see, 1.7. And the program will tell us this is an oblique shock. And M1 and M2 are this. Theta is given by this. And this is a shock relations, the relations across the shock. And this is the upstream isentropic relation. This is the downstream isentropic relation. All right, this seems to be all right. Let's say if we know beta is still 75 degree, and we do not know M1, we can use anything. We can just use enter. Oops, there's a problem here. Let's see what is going wrong. So M1 is none. Oh, it turned out that we cannot just use enter. We have to use anything that is not a number. So if theta we know is, oh, I forgot the value. If theta is 1, then yeah, you give us this value. So beta, let's try more. And Mach number is 1.7. And our theta value for this case is that number. And if we know beta is still 75 degrees, and Mach number 1, we don't know that. And theta is this number. Yep, we have beta to be, we have Mach number 1 is 1.7, the same. All right, this is correct. Now, we can use exit to quit it. Now, what if we know theta? And Mach number 1. Okay, we have to convert the value into radians. So theta is going to equal to value times degree to radians. What is the Mach number? We will ask the user to give us that. And if M1 is none, then something is wrong, right? We don't have to care about theta and beta are known, but M1 is not known, because that in that case, we can just give it beta first and then theta. And for here, and if we give it theta, then we have to give it Mach number. But if that is not given, then we use that. Else. Oh, it's returned, so we don't have to use else. But that's just personal preference. Else we can just print this. And our Mach number would be M1. Okay, let's give it a try. So theta is going to be 17 degrees. Right, Mach number is maybe 2.0. Okay, this is something that is wrong. Oh, here. It should be M1 and theta. Try again. Theta is 17 degrees. Mach number is 2.7, 2.3. It should give us two solutions. One is a strong solution. Everything seems to be all right. The other is a weak solution. And let's see if we have beta value to be that and Mach number to be 1.3. If that is giving us the same thing, beta is that, Mach number is 2.3. Yep, theta is 17 degrees, right? Okay, they are close. There might be a small error, but it's fine. It's accurate enough. All right, we are done with the oblique shock. Next is expansion waves. L if name is theta2. Oh, before we move on to expansion wave, we have to. I would like to make it possible for the user to change the constant. So, in case that the gas is not air, it might be helium or whatever. So, else if name is constant r, then we are going to use the global function, a global variable r, and r is going to be replaced by the value. And we will print out saying that, okay, change R to this value. Similarly, if gamma is changed, we are going to use gamma equals to value, and we are going to say, okay, change gamma to this value. Right? Okay, let's try. Okay, I'm going to say Mach number is 1.2. And what if we change the gamma to be 1.667? And then we try that again. So m equals to 1.2. It's going to give us different value, right? Different value for them. All right. And when we change it back to gamma equals to 1.4 and m is 1.2, we'll change back to our default value for, oh, sorry, I typed it wrong. Gamma is 1.4 and m2 is, m is 1.2. Yeah, this value, let's say temperature is 1.28, should be the same as the beginning. Yeah, 1.288. All right, let's continue to our expansion case. If theta2 is given, we still need to find m2, right? So m1 is going to be a prompt number. Again, if m1 is none, we are going to print, okay, wrong input format, because we have to know m1. Otherwise, we have this function with theta2. And our theta2 here is value, and m1. Okay, however, theta2 is again in degree, so we want to convert that into radians, degree to radians. And here we use theta2. Okay, let's try it. So the expansion angle would equals to maybe 12 degree. And M1 is a supersonic flow, so 1.9. It gives us new one, theta2, and Mach number 2. It seems to be correct. What's next? Quasi 1D. So if name is maybe AA, or name is AA star, right? I'm just going to print all of them from here. And let's give it a try. So if AA star is, it has to be larger than 1, so maybe 2. Yeah, it gives us the quasi 1D solution. The two solutions for Mach number, one is subsonic, the other is supersonic. And let's see if this one is correct. So if we give it back, if we give it back, Mach number is that. The AA star is indeed 2. And what if it's subsonic? Then M is that. Yep, it's correct. I think this is everything we have so far. And if name is none of them, we are just going to say, okay, the input is wrong. All right. So try again. Dot dot. Return. Or if the length of the input split by equal sign is larger than 2, or maybe it's 0, we print, okay, wrong input format, and try again. So let's try. And if we have a random thing equals to something equals to something, you say it's wrong input. So if we have a thing that is looking all right, P2, P1 equals to, it should be larger than 1, so 1.11. And we have another equal sign. This is weird, right? What does that mean? It means nothing. So it should give us, okay, wrong input format. Try again. However, if we have that, it should give us the correct response. What if we forget what kind of variables we have? It would be nice if we give it a, hold on. This one should not be wrong input. This one is correct. Oh, I think the problem is here. Oh, yeah, that is all right. So what if we forget what kind of variables we can have for all of them? It would be convenient to print a help message. And I'm going to print an example. For example, P2, P1 is 5.77, or Mach number is 10. So when we are running it, and we say, okay, Mach number is 8, and then we forget how to use the normal shock relation, we will just type question mark. It will tell us, okay, for normal shock relations, we just have M1. We can have capitalized M1 or small M1 to be 8. And then we find this really strong shock relations. And they are going to be the same if we use lowercase. So I think I will just end the video here. If you want, you can also add relay flow or 1D flow with friction. They are going to be similar to all of these cases. You just have to use more functions, and you will have to find solutions. And you probably need to find 2 solutions for some cases. I haven't read it yet, but it's not going to be really different from all of them before. For all of this, this one, finding beta from Mach number 1 and theta can be the most challenging one, because we will first finding theta max and the corresponding beta value, and then using bisection method to find beta. This one can be slightly challenging, but the rest of them are really straightforward. Okay, I'll share the code, and the link will be in the description. And thank you very much for watching this.